All right, so these are technically the notes starting for Unit 2. So we're going to start off, since we've talked a little bit about the particulate nature of matter, we're going to talk a little bit about how to classify matter. So when we look at everything in the universe that is matter, and remember matter is everything that has mass and takes up space, we can put it into two large groups, substances and mixtures. Okay? Substances are elements and compounds. And if you read in a textbook, it usually says something like there's a fixed composition. What does that mean? Well, it means basically that if you find a chunk of iron, all of the atoms in the iron are iron atoms. And if you find a sample of water, all of the molecules are going to be the same, and they're all going to be H2O. Okay, so those are pure substances. Mixtures are kind of difficult to describe. The best way I can describe it is they're combinations of two different things where the amounts can differ from place to place. And so I always share that when I was a kid, we always ate cereal for breakfast, and we usually had Raisin Bran. And my parents were very thrifty, and they bought sort of the generic Raisin Bran. And when we went over to my neighbor's house and had their Raisin Bran, they bought the name brand, like Post or Kellogg's. The name brand Raisin Bran has a lot more raisins in ratio to the flakes. It's a different kind of a mixture. They're both made out of raisins and flakes, but the name brand, and that was like, I was kind of like bitter about that for a while because I was like, man, we are not getting enough raisins. So pure substances have a fixed ratio. So when we talk about water, it's not like you can make water and have it be H3O or H2O4. It doesn't work that way. It's a fixed composition. Mixtures, on the other hand, they can have any kind of a ratio, okay? So here's a little table that kind of shows this relationship, how we classify matter. And so we've got matter up here at the top, anything that has mass and takes up space. And it can be broken down into pure substances and mixtures. And then the pure substances can be broken down into elements and compounds. Okay?
Define element. Is that the simplest form of matter?
Yeah.
We'll get there. Just be patient. Yeah, okay. So, 3 words that students get confused with, because the way we use them in everyday life is a little bit different than how we use them in chemistry. The 3 words are element, compound, and molecule. So when we use these words in chemistry, we mean specific things. So elements are made up of only one kind of atom. So if we look at a picture, a particulate picture, like we've been drawing, and there's only one color of circle, it's an element. Okay? A compound is 2 or more atoms of different elements that are stuck together. Molecule is kind of a generic word for like anytime you have 2 particles stuck together, a chemical bond between the particles, it's a molecule. So if I wanted to represent an element, I could draw a dot, or I could draw 2 of the same dot stuck together, right? If I wanted to model a compound, I would have to draw 2 dots that were stuck together that were different from each other. Okay. Now, these two, this one and this one, these are both molecules because they have two atoms stuck together. So molecules can be elements or compounds. Elements can exist as single atoms or as molecules. Compounds are always molecules, okay? So those are just that's some terminology that you should make sure you've kind of got straight in your head. So, like Travis said, the smallest particle of an element is an atom. The smallest piece of matter that you can have that's still an element. The smallest particle of matter that you can have that is still a compound is called a molecule.
Did you hear about BB Box coming to fill your room? I don't know if you.
Wait, what?
Wait. Okay, so elements are represented by symbols. And you may be familiar with the symbols for the elements from the periodic table. The symbol is always an uppercase letter or an uppercase letter followed by a lowercase letter. It's never two uppercase letters, never two lowercase letters. It's either one uppercase or an uppercase and then a lowercase. These are symbols. Okay, so everyone around the world, no matter what language you you speak, you recognize this is sodium. It doesn't matter. Okay, if you speak Russian, if you speak Chinese, if you speak French, that's sodium. Okay, so these are symbols, not abbreviations. We've got to keep that in mind. Compounds have formulas. And so NaCl is a formula, okay? Do you remember when you were a little kid and you were first learning how to spell words, and sometimes you didn't always put your letters together right? Oh, please, I'm sure you do.
Not yet. I'm still learning.
Still learning. Okay, well.
It's always good to keep learning.
Yes, it is. Okay, so this would be an example of a symbol. This would be a sample of a formula, okay? And so when we write formulas, we want to write our symbols correctly, just like you would want to write your alphabet correctly. And we want to write them close together to show that they are together, okay? Now, elements have symbols and compounds have formulas. But sometimes there are formulas that look like this. Okay, so that's Cl2. What that means is that I have two chlorine atoms stuck to each other. Okay, it's an element. Oh, it's right underneath that thing, isn't it?
Chloride?
It would be chlorine.
Chlorine.
Yeah. Okay. So that's an element, and it's a molecule. And we call that Cl2 a formula. Okay. This one is a formula. It's a molecule, and it's a compound. Okay, because it's got two different elements together. And this last one is a symbol and an element, and it represents one atom of the element. Okay? So in a lot of ways, this first quarter is like a foreign language. You're going to be learning the language of chemistry. Okay? So, in nature, there are 118 elements that we know about. The last, 116 through 118, we've just discovered recently. Okay, and we'll talk later about how we go about discovering new elements. Only 93 of our elements actually occur in nature. The other ones we have synthesized in a lab. Compounds, there are millions and millions of compounds, and even more molecules. Everything around you is made up of some kind of a mixture or a compound, mixture of compounds and elements. There are lots of compounds that we have not discovered yet, and that's one of the concerns about the fact that the Amazon rainforest is disappearing. They have found some really interesting plants that they never knew about before, and they found chemicals in those plants that they think might make medicines. So, the cure for cancer might be growing in the rainforest right now. And if we harvest all the plants and kill them all, we could lose out on that. So it's really important for us to preserve that area so that we can find out those things. They still don't know. People have smoked tobacco for hundreds of years. I don't think that they have yet identified everything that's produced when you burn tobacco. They don't know all of the chemicals that are produced. They're still figuring that out because there are so many things that can happen. All right, so here's some examples. Elements. We've got our uppercase letters or uppercase, lowercase. We've got our molecules that are elements like H2 and O2. Got our compounds that have more than one chemical symbol in them. And then we've got our molecules. And remember, molecules are just sort of a generic name for any time you've got two or more atoms that are bonded together or stuck together. H2O.
NH3.
So H2O is water. NaCl is sodium chloride, which is table salt. NH3 is ammonia, which is like in window cleaner. And NaHCO3 is baking soda. And we will learn when we look at the periodic table, when we learn about the periodic table, there are some elements that like to be in a pair. They never like to go like one atom. So there are certain elements like we see here, hydrogen and oxygen, also chlorine. They don't like to, in nature, they are not found as individual elements. They're either in a compound or they're paired up with another element of the same kind, another atom of the same kind. Okay, so here's a little picture that might help when you're thinking about things like those particle diagrams in ChemThink. So notice at the top with the elements here, the way I can tell it's a pure substance is if I start circling the individual particles, all of the individual particles look exactly the same. Same thing here. Every particle looks exactly the same. Down here with the compound, every particle looks exactly the same. That makes it a pure substance. Okay? If I start circling particles and they don't look the same, I have a mixture. Okay? Okay. So now if we think of element symbols as our alphabet and formulas like our words, then chemical equations are our sentences. So this is a chemical sentence. It's representing something that actually happens. And so learning to write chemical equations is a big part of learning the language of chemistry. So we've already talked about element symbols, represent an element. First letter is always capital. In this particular chemical equation, we've only got 3 elements: carbon, hydrogen, and oxygen. Does anybody know what this chemical equation represents?
No clue.
What do you think it represents?
Air.
Well,
To be honest, I have no idea.
that.
Is it really? Flame?
Yes. Well, it's butane.
Sure.
It's burning butane. So the fuel in this lighter is butane. So what's happening here with this lighter is represented by that chemical equation. Okay? So anytime we write a chemical equation, it is representing something that really happens. Okay? So that's why we're picky about how we write them, because they represent real life.
O equals oxygen.
Okay, so we already know chemical formulas. In this particular reaction, we've got C4H10, which is butane, and O2, which is oxygen, CO2, carbon dioxide, and H2O, water. So those are our chemical formulas. So I'm going to talk to you while people are writing now. I want to tell you that you're doing a great job. I know we're not very far into the year, but I'm really proud of you that I don't see a lot of people looking at their phones. It's really important that you accept responsibility for that. Because this is a college prep class and you are upperclassmen, I refuse to be the phone monitor, okay? Because if you are going to college, your professor is not going to monitor whether you are on your phone or not. Okay? You might as well start practicing now and learning how to discipline yourself so that you are not constantly looking at your phone. It's a distraction. And it's rude, to be honest, it's rude to be looking at your phone while someone is lecturing. But you know, when you go to college, you pay, I don't know, a lot of money, $75,000 a year, and they have your money. And so in the professor's mind, if you want to look at your phone the whole time and fail the class, oh well, they have your money. They'll take another $75,000 for you to retake all those classes. So you have to learn to accept responsibility for your education. And you guys are doing a good job, and I'm really proud of you because that's a huge temptation. So then people always say, well, what do I do? What if I'm done writing and everybody else is still writing? What you should do is you should look back. You should scroll back. I know that sounds really nerdy, but the more times you look at it, the better it's going to stick in your brain. And so looking back and saying, oh yeah, this is a molecule, this is an atom, this is a compound, just reading through that again while other people are finishing writing, that's going to be a lot of help, okay? Also maybe quiz yourself, say, okay, we're talking about atoms and molecules and compounds. Can I say in my mind what those things are? Okay? So that's the kind of stuff you can do as other people are finishing writing, if they're writing more slowly than you are, okay, instead of snapping your friends or watching TikTok.
Snapping your friends.
Yeah.
TikTok.
Yeah. Okay, so subscript. The subscript are these little numbers. You can think of like the prefix sub means down. So like the subway is underground. Okay, so the subscripts are down and to the right. So the 4 in C4H10 goes with the carbon. And it tells us that we have 4 carbon atoms in that molecule. Okay?
Number written.
So this 4 goes with the carbon, and the 10 goes with the hydrogen. So this is C4H10. 4 carbons, 10 hydrogens in the molecule. And those little numbers are called subscripts. Not to be confused with superscripts. Okay, so if you have trouble remembering, sub is like the subway, and you go down to the subway. A superscript, like Superman, is up in the air, so a superscript is going to be up. Subscript is going to be down. All right?
C4H10.
Okay. So,
Coefficient.
now the other numbers that you see in a chemical reaction are called coefficients, and they work just the way that coefficients work in algebra. Okay, so you know that like in algebra, if you have, let me get my pen out here. If I have 2 times 2x plus 5, that 2, multiplies everything, multiplies through, right? So we get 4x plus 10. Remember that from algebra? Okay. So when I have a coefficient of 2 in front of a compound, just like the distributive property in algebra, this is going to multiply the whole thing. So it means that I have 2 C4H10s. So I can say that means
2C4.
I've got 2 of those. And I can say in those 2 C4H10s, I have a total of 8 carbons and 20 hydrogens, right? Okay, so the coefficient works just the way it does in algebra. And it's called the same name, so that's kind of nice. Okay, so the chemical equation is this whole shebang here. It does not have an equal sign because it's a change. The substances that are on the left side of the arrow are different from the ones on the right. They have different properties, okay? It's kind of like chemical changes are kind of like if you ever had one of those Lego sets as a kid that you could like put it together one way and you had a car, and then you put it together another way and you had a transformer, and you used all the same pieces, but you could make 2 different things. That's what a chemical change is like, okay? We start out on the left and we have certain number of atoms that are like our Legos. And what we do is we break them apart and rearrange them to make the things on the right side of the arrow. So there's a change.
We did it on 2.
What?
Draw that. I got it.
All right.
We don't have arrows on
Yes, sir.
Will we be able to find this on Canvas, the actual presentation itself?
Yes, I'm recording it right now. All right. So, oh, sorry, I'll go back.
You're fine, you're fine, you're fine, you're fine. I think I can just see it up on top. Okay, thank you.
Okay, so like we said, the chemical reaction is what is actually happening. So in this case, it's the combustion of butane or the burning of butane in oxygen. So the exploding can was also an example of a combustion. So you may remember from freshman science that the things that we start with are called reactants. So it's really important to remember this because we refer to the reactants and then the products a lot. And I don't always remember to say left-hand side of the arrow. So you need to know the reactants are what we start with. It's on the left-hand side of the arrow. They are our starting substances. And if a certain element is not in the reactants, it can't be in the products. If a different element shows up in the products and it's not in the reactants, then either there's a typo or you're not doing chemistry, you're doing physics. Okay? Because in chemistry, the elements don't change. Right? If we get a chance to do some nuclear chemistry and talk about nuclear reactors, we'll talk about what happens. But in general, in chemistry, our elements don't change. Okay? So our products on the right side tell us what we have produced, what we've made. There are the same elements in both the reactants and the products. If there's not, then either there's a typo or you're not doing chemistry. Okay? And so, of course, the arrow means a change. We've got a change happening. Something new is produced. And we can tell because the properties are going to change. Okay, so the reactants each have their own unique properties, and the products each have their own unique properties. And so we can do certain tests to see if something has changed. And we balance the equation because that's the way matter works, okay? Like I said, it's just like the Lego set. You've got a certain number of Legos, you put them together one way, you break them apart, you put them together another way. You still have the same number of each type of Lego. And that's why in this particular reaction, if you take the time to count them up, there's 8 carbons on both sides of the arrow. There's 20 hydrogens on both sides of the arrow. And there's 26 oxygens on both sides of the arrow. None of those atoms are lost or destroyed. They're just rearranged. And so we balance equations because that's the best symbolic representation of what really happens. Okay, so when we read this, we say, for every 2 molecules of butane that I burn, I'm going to need to react them with 13 molecules of oxygen. It's going to produce 8 molecules of carbon dioxide and 10 molecules of water. Later on this year, we'll say, well, what if I burn 4 molecules of butane? How many molecules of water will I produce? So if I double this, what do you suppose happens to this? It doubles, okay? So if I burn 2 molecules of C4H10, I get 10 molecules of water. If I burn twice as many, I get twice as much water. Okay, so there's a relationship. And we can predict how much product is going to be made. So I sent out an assignment that these are your element symbols. Make sure that you write them correctly. It's really, really, really important. Some things that I see very often that you should not do. So this is like what not to do. Don't do this. Okay, that's not an uppercase and a lowercase letter. That's 2 uppercase letters. One's just written smaller. Okay? That is not an uppercase and a lowercase letter. That's 2 lowercase letters with a big lowercase n, right? And then iodine is like this. Otherwise, if we write aluminum with iodine, it looks like that. And it's confusing. Okay, so our iodine always has those little bars. So those are the ones that people mess up the most when they're doing their element symbols. This should actually be I3. Notice a lot of these you probably already know, like hydrogen and oxygen. Okay? So they're 50, and the quiz over these is going to be a week from this coming Monday. So whatever that day is. Out of the 50, I'm going to choose 15 symbols, and you have to write the names, spelling them correctly. And then I'm going to give you 15 names, and you have to write the symbols correctly. Okay, so it's going to be kind of picking from this list of 50. And, you know, there's lots of ways to do this. Some people like flashcards. Sometimes even just making the flashcards will help you remember. There are probably a gazillion Quizlets on this. Probably some people even made, you know, by Bradley High School students that have the same elements on it. The way I like to study when I was memorizing things is I would print this out and then I would like cover the symbols and look at the names and try to write the symbols and then check it. And then I would go and go back and cover the names and, you know, try to write I'd go back and forth like that. Because for me, looking at something and writing something helps to stick things in my memory. For some people, hearing it helps them remember. And so having someone quiz you, that can help you remember. There are lots of little tricks to help remember these, and we'll talk about some of those next week. So you need to get started on memorizing. Well, you know what? I'll just tell you some of them right now. So like lead is PB, which is really weird. And the only reason why it's got such a weird symbol is because we've known about lead for a very long time. And so the original language of scholars was Latin. And so what they called lead was plumbum. So it's PB. Okay? So yes, and so you can say, you know, like peanut butter and bread, peanut butter and lead. Aha, yeah. Okay.
Don't eat this together.
Yeah, that's right. Don't eat it together. Another one is like AU is gold and AG is silver. So like if somebody ran by and stole your necklace, you would say, AU, that's my gold. And then he would look at it. He would look at it and he'd go,
What is this?
and he would go, "Aw, gee, it's only silver."
That's actually good.
Oh, come on. Core chemistry.
Yep.
Those are good.
Let me see. If you've ever worked in a shop, the things that you use to cut metal are called snips. Okay?
Yeah.
And the symbol for tin is SN.
Oh,
Like a snip. Let's see.
there was no corny joke on that.
Sorry.
No, those are actually pretty good.
Oh, there we go. There we go.
Travis doesn't know what comedy or humor is.
Well, this one up here, this is kind of weird, but like, if you look at, this is antimony, but it looks kind of like Auntie's money. Who would be trying to get Auntie's money? Your sibling, SB. Yeah. Okay. So,
That far gold is my favorite.
I'm not going to torture you anymore, but I am going to show you this because,
Be backstage, who's told you about
okay, there we go.
this? And I kind of immediately.
Well, you don't have to.
No, I will.
You
Because
would
like now, like, okay.
So this is your party trick. So
Yeah.
okay.
It's very long. Basically, just give a big shout if you know who Tom Lehrer is.
Yes. No, over there. Yes, there could be more excited.
Okay. Tom Lehrer, in my opinion, is the cleverest and funniest man of the 20th century, and he's kind of my hero. And he wrote a song called The Elements because he was a scientist, and it's the name of every element in the periodic table. And that's my party piece. It's quite long, so do stop me if you just get bored.
Okay.
But I will. This kept me up last night. I was so nervous about doing this.
Well, do I feel bad now?
No.
Okay. So.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and uranium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and anthium, and osmium, and acetine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, and terbium, actinium, rubidium, and boron, gadolinium, and iodine, iridium, and silicon, silver, and barium, bismuth, bromine, lithium, beryllium, and barium. Let's start the next verse. There's holmium, and helium. Helium and hafnium and erbium, phosphorus and francium and fluorine and terbium, and manganese and mercury and molybdenum, magnesium, dysprosium and scandium and cerium and cesium. There's lead, praseodymium, platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, potassium, chromium, cerium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, arsenide, and beryllium, and argon, radon, neon, and argon. Hold on, quiet. Argon, radon, neon, krypton, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. Now,
There you go.
Jeez.